Welcome to the Archean Eon, a mysterious time over 2.5 billion years ago. Earth was a vastly different world, one still taking shape. Imagine a planet nearly covered in vast oceans, under a thick, hazy atmosphere filled with volcanic gases. Sunlight struggled to penetrate the dense clouds, casting an eerie, muted glow over the water-covered surface. Volcanic islands occasionally broke through the waves, steaming and venting gases, setting the stage for a long process of transformation. Formation of stable continental crust. As Earth's surface cooled, molten magma gradually solidified into the first stable crust. This was not a smooth process. Early Earth was violent, with constant volcanic activity, intense heat, and meteorite impacts. The crust that formed was unlike today's continents. Picture small, rugged islands of dark, jagged rock, surrounded by steaming oceans. These proto-continents were unstable, often melting and reforming due to the planet's internal heat. Yet, over time, the cooling process allowed some sections of crust to remain intact, laying the groundwork for more permanent landmasses. The role of plate tectonics. Earth's tectonic plates were also beginning to take shape during the Archean Eon. Though different from today's tectonic activity, the constant movement and collision of these plates played a key role in Earth's transformation. When these plates collided, they pushed up sections of the Earth's crust, creating rugged terrain. Volcanic eruptions released minerals and gases into the atmosphere, gradually enriching the environment with essential elements. These processes created the foundational building blocks of the Earth we know today, with the formation of the earliest, most primitive continents. The first oceans and the emergence of life. With the cooling of Earth's surface, water vapor in the atmosphere began to condense, forming the planet's first oceans. These early oceans were turbulent and filled with dissolved minerals from the surrounding rock. They provided a stable environment for the development of Earth's first life forms. Simple, single-celled organisms, ancestors of modern bacteria, emerged in these waters. These primitive life forms were incredibly resilient, thriving in the harsh conditions of early Earth. They adapted to the mineral-rich, oxygen-poor environment, finding ways to survive in the midst of volcanic activity and extreme temperatures. Hydrothermal vents and the cradle of life. In the depths of the oceans, hydrothermal vents spewed hot, mineral-rich water from beneath the Earth's crust. Scientists believe that these unique environments, full of dissolved metals and chemicals, may have provided the ideal conditions for life to evolve. The combination of heat, minerals, and water created a perfect environment for chemical reactions that could lead to the formation of simple, self-replicating molecules, the very first steps toward life. This discovery is crucial in understanding how life might evolve in other extreme environments, such as on distant planets or moons with similar conditions. The evolution of cyanobacteria and photosynthesis. Then came a turning point, the evolution of cyanobacteria. These were no ordinary bacteria. They had a revolutionary ability, the capacity to perform photosynthesis. Through this process, cyanobacteria absorbed sunlight, carbon dioxide, and water, creating energy and releasing oxygen as a byproduct. Although simple, this development was monumental. Cyanobacteria colonies formed structures called stromatolites, layered mounds of cyanobacteria and sediment, which are still visible in ancient rock formations today. These tiny organisms began to alter Earth's atmosphere, slowly but steadily introducing oxygen into the environment. The Great Oxygenation event. As cyanobacteria continued to produce oxygen, the concentration of this gas began to increase in Earth's oceans and atmosphere. Initially, this oxygen reacted with dissolved iron in the oceans, creating iron oxide deposits on the ocean floor, a process visible today in banded iron formations found in ancient rocks. Over millions of years, this gradual increase in oxygen would lead to one of the most significant events in Earth's history, the Great Oxygenation event. This slow, transformative process changed the atmosphere, turning it from one dominated by gases like methane and carbon dioxide to one with increasing amounts of oxygen. Formation of the ozone layer. As oxygen levels rose, the formation of an ozone layer began high in the atmosphere. This layer was crucial, as it provided a shield against harmful ultraviolet (UV) radiation from the sun. Before the ozone layer, Earth's surface was constantly bombarded by intense UV rays, making it nearly impossible for complex life to exist. With this new protective layer, Earth became a much more hospitable environment. The stage was set for life to eventually move from the oceans to land, and for more complex organisms to evolve in the eons that followed. Impact on Earth's climate and environment. The oxygenation of the atmosphere had far-reaching impacts on Earth's climate and environment. The increase in oxygen led to a cooling effect, as methane, an extremely potent greenhouse gas, was broken down in the presence of oxygen. This cooling could have contributed to a period of global glaciation, sometimes referred to as snowball Earth. Though this remains a theory, it highlights the profound influence of biological processes on the planet's climate. The interaction between life and Earth's atmosphere was already reshaping the planet in ways that would lead to an even more diverse and complex biosphere. Legacy of the Archean Eon. The Archean Eon was a time of profound transformation, a period when Earth went from being a chaotic, inhospitable world to one with stable land, vast oceans, and a slowly oxygenating atmosphere. It was during this eon that the foundations of life were laid, with the emergence of cyanobacteria and the buildup of oxygen, an essential ingredient for the development of complex organisms. Without these ancient processes, the explosion of life in later periods, including the appearance of plants, animals, and eventually humans, would not have been possible. Conclusion: the blueprint for life. The Archean Eon serves as a blueprint for the essential conditions that make a planet habitable. The processes that occurred over billions of years, cooling, the formation of stable land, the advent of life, and the transformation of the atmosphere, highlight the intricate balance required for life to evolve. It was a period that bridged the gap between an uninhabitable, molten planet and a world teeming with life. This ancient eon reminds us of the delicate balance of forces needed to sustain life, a balance that began over 2.5 billion years ago.